Hi.
Hi. Hello. Uh, I guess we have a couple of guys, a couple of students are still joining in.
Sure, we can wait.
Wait for like 2 minutes and we'll begin. Cool. Let us begin. Uh, all the attendees we have, let me introduce Kaushal here. Kaushal is joining us from USA. Uh, it's an odd time there, I know. So he's awake for all of us. Uh, it's almost like 2 o'clock, right?
Yeah, it is exactly
Yeah.
true.
So we are glad to have Kaushal on board with us to take us through a lot of the world of synthesis. Recently, I've been teaching electronic music production to a couple of students, and we were all going through the journey of understanding synthesizers, additive and subtractive synthesis, FM synthesis, and all that.
Hmm.
It is lovely to have you on board, Kaushal, because this kind of knowledge that you impart about synthesis and coming from a researcher like you is going to be beneficial for our students as well. So, without any further delay, let's get started with the session. And over to you, Kaushal. You can start.
Sure. Thanks, Mohit.
Thank you.
All right. Hello, everyone. I am Kaushal. I'll introduce myself briefly. Actually, I think I should start sharing my screen. Just a sec. All right. I hope you all can see the presentation. Okay. Um, yeah, so I'll introduce myself briefly. I am Kaushal, and I am a computer engineer. I specialize in audio software development. So I recently graduated with a master's in music technology from Georgia Tech, and I'm like now looking to build a career in audio software development. Um, so I so in this presentation, first of all, I will be talking. I'll tell you a bit about myself, what all I've done, and my experience here at Georgia Tech, um, and in general in the field of music technology. I'll also show you like what is going on, like what is the bleeding edge research that is going on in the field of music technology. Um, After that, like before getting into audio synthesis, I would really like to dive a bit into the history of electronic music, and experimental music, because I think that this is really essential if you when you are trying to learn about audio or electronic music in general. And this kind of history gives you a real um, perspective as to what you are dealing with. Um, so after that, we'll do a demonstration with VCV rack, which is a software which is software which emulates a hardware modular synthesizer. And if we have time after that, I'm going to show you some examples of live coding, which is like creating music through code, live on or using your laptop. All right, so let's start with it. Okay, yeah. So I am from Pune, and I have a bachelor's in computer engineering, and I got it at a VIT Pune, which is in Bibwewadi. And it was a really nice experience. I actually really like programming, and that was the reason I decided to pursue computer engineering, because I feel like I enjoy the process of like going from point A to point B, given a certain set of tools. And I find that whole process really interesting. And programming is all about that, trying to find a solution given a set of tools. So basically, you're just going from point A to point B with the best approach possible. And I think this translates a lot into also the way modular synthesizers work and the ways you can go about it. So at at VIT, I also am a musician and I play the violin. So at VIT, I was involved in Firodia Karandag, where I actually met Mohit. And Firodia Karandag is, if you don't know, it is basically a theater competition which involves live music on stage. So you have to like play the songs and give background scores to the whole for the whole play. And during this time, I met Mohit, and I have to say, like, Mohit is really a good teacher, and you guys are really lucky because he's really talented. And initially, when I began my journey for electronic music, I being a classical musician and just playing the violin, I had no clue about what goes in electronic music and what all there is. And I also had like a really narrow view of music. I was mainly I used to listen to mainly like classical music and rock music and mainly instrumental focused music. And I had this vision of vision that not a vision, but I basically had this perception that electronic music is not at all like there's no talent involved in it, and I was so wrong. I was so wrong. I had this prejudice which I was not able to get out of. But as I started exploring this field, I realized that this is so much. There is so much more to electronic music, um, and yeah. Uh, One of the most influential things that changed my perception about this was a course that I did at Georgia Tech. We had a course called Music Technology History and Repertoire, which discussed about the electronic music and which discussed about how electronic music evolved and uh, how experimental music evolved and how that pushed the boundaries of art. So after my graduation from bachelor's at VIT, I briefly worked for like about an year as a software engineer, and then I went on to pursue my master's at Georgia Tech. Um, so before I get before I proceed, I want to give you this advice that please keep an open mind. I think this is the best advice I can give you, because if you're closed to if you have like a narrow focus, or if you think like, okay, this I like this genre, so I'm going to be working with only on this genre, then you are restricting yourself of so many possibilities that there can be. um, and it will help you like having an open mind will literally help you to grow artistically and not just technologically. All right. So, yeah. So I started my master's at Georgia Tech about in 2018, like 2 years ago, and Um, I graduated this May. Uh, so mainly the program at of music technology at Georgia Tech is very research focused, and here basically I learned stuff like digital signal processing, music information retrieval. Um, and interactive music and music tech history and stuff. And over the period, over the course of my master's here, I developed a lot of interactive musical web applications. I have also developed an audio software, a MIDI player, which I'll show you short demos after this. But yeah, I have to say, like after doing this course, I've literally I can say that I've grown as an artist and not just technologically. So Georgia Tech Center for Music Technology is the research institute in Georgia Tech, which is around which this whole music technology program is built. And being a part of the music technology program, you have to take part in the research at this institute. So, so my main research focus here was in music information retrieval. And mainly I worked as a researcher in deep learning for replicating audio effects. So I'm gonna go to my website and show you some short demos of what all I've worked on. Okay, so so one of the projects that I had worked on was a MIDI editor, which is a really basic, like the minimal MIDI editor that you would need. So you can just open any MIDI file in it and just play it, and it would. I hope you can hear that. So basically, it just plays a MIDI file with by using general MIDI, which means that it can map all the instruments based on the MIDI messages inside. So you get like the whole thing and not like the whole instrument setup and not just one instrument or just like a piano that it is mapped to. So this was one of my projects. Another interesting project that I had worked on was Groove Machine. So Groove Machine is a teaching tool for children, and it is a tool to get people interested in computer science. But the way it does it is that it does it through music. So for uh, Groove Machine is a sequencer. It is it is a step sequencer where you can place different blocks onto the sequencer, and depending on what you've placed, it generates music. And for every action that you do, it shows a visualization of the code or some sort of like a programming a code line that replicates what you've done. So hold on, I'm gonna make this full screen. Yeah, so you can see that you can. Yeah. So for every action that happens here, you see some sort of code that is generated over here. And all of this is built using a language called, not a language, but this is built in JavaScript. But there is this one framework which allows you to build all these components and generate these sounds using audio synthesis. For this specific project, we used a sample-based approach where each block is associated with a sample, but then all these red, yellow, green, and red, yellow, and green and orange blocks that you see, those modify the sound or through some sort of filtering or some sort of like reverse effects or stuff like that. Um, Another one of the projects that I worked on was this was more of like a musical art piece where you have these different blocks and different balls, and when they hit each other, they make sounds based on the size. Like what I do is I abstract different properties of these balls. Like I take the different properties, and depending on their interaction, music is generated. So you get something like. Right. I'm just going to move through these a bit faster so that we have more time later for VCV rack. So I'm just going to give you like a short overview of this. Um, and yeah, for my main research, what I worked on was one of the projects was generating impulse responses. And impulse responses are really useful for stuff like generating reverb. So there is this thing called convolutional reverb, which uses some sort of short signals, which are impulse responses, to to recreate the acoustics of a room. And I was trying to generate these impulse responses using deep learning. I'm not going to get into the details of that because then we would be here forever. But yeah, that was one of my projects. And another one was trying to model equalization effects using neural networks. So what I was trying to do is if you have an audio filter, excuse me, if you have an audio filter, I was trying to learn what sort of EQing or what sort of filtering that filter is doing. And based on basically, I was trying to create a copy of that filter using a neural network. So if you have like an input signal which sounds something like this, and the target signal is this, like this is the input, this is what happens after filtering. So my program would learn this and be able to apply that to any signal. So if I do it on the same original input signal, my program would predict it to be this, which here you can see closely matches the filtering of that filter. Yeah, that is about it. All right. Um, yeah, so that is what I have done at Georgia Tech. But there is much more that is going in the field of music technology. So there are these five things that you see are these are the five labs that are there at the GTCMT, Georgia Tech Center of Music Technology. And there is some amazing stuff going on over there. So there is this one lab called Musicianship Lab, which builds robots that play music. And I'm going to show you like a really short video of that, of this one robot called Shimon. There is this video actually. Yeah. I'm just going to skip through this, but I'll talk over it and tell you what it is. So Shimon is a marimba playing robot, which actually who can listen to you, and based on what you are playing, it can decide what notes have to be played, and you can basically jam with it like another person. So just check this out.
Robots. I'm still not feeling completely comfortable calling myself roboticist. I'm a musician at heart, but obviously robots is where I try to find the creative outlet. So today we are here at Georgia Tech Center for Music Technology. This is a robotic musicianship lab where we develop robotic musicians and new musical instruments. Robotic musicians can listen to music, they understand music like humans, and then they improvise, but they improvise like machines in a way that hopefully would inspire us to play music and think about music in new ways. We're also developing new musical instruments that will allow humans to interact with robots, such as a guitar that you've just seen.
This instrument is the voltage-controlled guitar. It was built as part of the Moog Hackathon, which was a student instrument design competition.
All right. So yeah, that's the thing. And in the last part, what that person was talking about, the Gutman thing, the guitar that he built, is actually a part of Moog Hackathon, where you're given a synthesizer and you have to build an instrument based on that. Um, so let's go to that. So Moog Hackathon. So this is a big event where you are given a synthesizer, which is really basic Moog synthesizer, which has an oscillator, filter, and a, a low frequency oscillator and an envelope generator. So I'm going to get into what exactly these components are, and we're going to explore how all of these components work. Um, but for now, you can just like see what they are. So using this, people build different instruments. So you can get something like, you have people building instruments like,
I see nothing.
and something like this. So in all of these instruments, the core or the base synthesizer is the same, but the way people interact with all these different components of the synthesizer and connect them together is what creates the beauty of it. So this is another instrument which was built based on the Moog, and here you can see like all of these components are extracted into different into a larger thing and connected together. So I'm not going to play this video actually because I think we might run out of time if I do that. But um, in essence, like this is what this Moog hackathon is about, and this is how you can utilize synthesizers to generate your own, not only music but your own instrument. Okay, so let's get into music history a bit. This is actually my favorite subject. Electronic music history is really amazing, and I would like to recommend, like, if you can get this book and do read it. It's called Electronic and Experimental Music. It's by Tom Holmes, and this is the best book ever. Um, like reading this book will give you a perspective and like will change your perception about the way you look at electronic music. So for electronic music, the earliest thing was a telharmonium, which was a huge could say a synthesizer, which are these tone generating wheels, and it was used like uh, to transport that thing you would need like 30 railroad cars, and this was back in 1896. So this was an inspiration for a lot of things, and there was this one person who was a proponent of microtonal theory, of microtonal music, and after seeing the telharmonium, he said said that there are so many possibilities, and there is this line that the pitch depends on a number of vibrations, and the apparatus may be set to a number desired. The infinite gradation of the octave may be accomplished merely by moving a lever. So what he wanted to do is um, divide, like we have an octave, and in an octave there are 12 semitones, but he asked like why just 12 semitones, why not 13, why not 14, why are we just keep being bounded by these rules that we have created, and why not explore? And I think this is the core value of experimental music, that you ask the question why. So this gave rise to actually like the people who supported this were called futurists, and they had this ideology of noise. And so Luigi Russolo was such a futurist, and he wrote this manifesto called The Art of Noise, which was literally a declaration, it was like a declaration of war onto on the traditional shackles of the traditional music. And it said that uh, every sound is music. Like why do you say that why can't we accept all sounds as music? And it, basically they advocated the complete destruction of musical order by celebrating noise as music. So from experimental music, we learned that the focus shifted from merely playing the notes to the creation of something much more fundamental, which is the sound. Like you weren't just looking at what you want to play, but like how it would sound and how to generate this sound object. And the focus also shifted on the process that leads to the sound creation. And I think these two, the process and the actual sound creation, these are two really important things that we need to keep in mind. And even in analog synthesis, analog audio synthesis, the process and the kind of sound object that we are generating is very important. So yeah, and sound was accepted for what it is without any expectations of it being anything. Like each sound is its own, and it can exist, and you just accept it for what it is. This was actually ideology by a very famous experimental um, musician called John Cage. There were two schools of thought. One was Elektronische music, and other one was music concrete. So again, in so that we don't run out of time, because I really want to focus more on um, VCV rack. I'm not going to get into the details of this, but basically, these were two different schools of thought, and both relied heavily in their own ways on the process in which a sound has to be created. So, music concrete was something that uh, was based on like sampling of sounds and then making music from that, whereas electronic music based on like using was based on using different components like oscillators and filters and creating pure tones and making music from these pure tones. So okay, so finally we come to synthesizers. The RCM R2 was one of the first synthesizers which used one of the first, not one of the first, but actually it was a great achievement. Like it was a technological achievement of its time. And later on, it was overshadowed by Moog and Buchla. But this is one of the very famous synthesizers that was ever built, and which used punch cards to tell for it. It used punch cards which would notate how the attack decay and note duration of the music should be. So I'm just saying these attack decay terms right now, but I'll explain these when we are doing working with the VCV. Okay, voltage control. So voltage control is the essential crux of modular synthesis or synthesizers. So what voltage control means is that um, you, depending on how much voltage you provide, you can change the characteristics of how an electronic component works. For example, if you have an amplifier like a voltage controlled amplifier, the by changing the voltage you could technically make it work as like the voltage works like a volume knob. If you supply higher voltage, it will generate a higher amplitude. For lower, it will generate a lower amplitude. And this is the essential crux of modular synthesizers. So in modular synthesizers, you have individual modules which do a specific thing, like an amplifier, an oscillator which generates a wave, um, a VCO, VCF. And these modules are just connected by different patch cables. And this is the beauty of it. You are generating the process, or and you are shaping the sound however you want. Okay. So we let us switch to VCV rack now, and I will show you some examples. Before that, I'm gonna show you the website for VCV rack. So VCV rack is a software. It is a DAW, but for modular synthesizers. And if you go to vcvrack.com, you can download it for free. This is an amazing software because if you want to buy like an actual hardware synthesizer, it costs a lot. And this is free, and you get all like the same quality of the components, and you can generate the same music, and you have much more freedom here. Um, but the only drawback is that you don't have the tactile feedback, and that is actually a big thing. But still, like if you are a beginner, and this is the best way to get into modular synthesis. So you can just create an account, and there are countless modules or countless third-party lab creators of these modules which you can download for free. All right. So when you open VCV rack, this is what you will see in the beginning. So by default, it gives you some modules, and when you play, okay, hold on, need to change the device. Okay, I hope you can hear this. Oh, all right. So what I'm going to do now is I'm going to remove all of this, and I'm going to start from the basics, very basics. So we need the scope. All right. So let's start with the most basic component. Okay, by the way, like I hope you guys can hear this. If you cannot, Mohit, please you can send me a message if I need to do any configuration.
Kaushal, we can hear this.
Okay, that's awesome. Okay, so VCO stands for voltage controlled oscillator. So an oscillator is something that generates a wave. So let's see what a sine wave looks like, and let's see what a sine wave sounds like. No. So this is what a sine wave sounds like. A sine wave is the most basic component. So a periodic or musical sound is made up of sine waves, and it is made up of different frequencies of sound waves, which are called as harmonics, which I'll explain in a bit. But now, okay, so you have a frequency knob. So if you increase it, you can even see in the scope that the wave gets like the bit decreases, like the wavelength decreases.
Can you hear us?
Yeah, I can hear you.
Yeah. So the thing is, the VCV is kind of louder than your voice. So could you just take down the VCV volume?
Oh, okay. Yeah, I'm sorry because yeah, if it is loud, please let me know, because I cannot know if from my end how loud it is.
Yeah.
Is it
perfect.
good now?
Yeah.
Like, can you hear VCV and me at the same time?
Yeah, we can hear you. Just that sometimes VCV suppresses your voice. So
I see. Okay, so what I'm going to do is I'm going to try to mute VCV when I'm talking. Okay. So yeah, so this controls the frequency, and you can accordingly hear it. So VCO will generate a frequency which is audible, but there is another type of component which is called the LFO, which means low frequency oscillator. So if we get the component here, oh, by the way, when you're doing this, if you press space enter, it opens this dialog box where you can just type in the name of the component that you want, and based on like how many components you've downloaded, it shows which one you want to pick. So I just picked the basic one right now. So now you have a VCO which looks like this. Let's see what a LFO looks like. So I'm again going to take a sine from the LFO, and you can see that here it is like really small. I'm going to zoom out now from the time I'm using this to zoom out in the scope. So here you can see it is basically just a sine wave, same as this, but you cannot hear this. Like if I plug this in here, you won't be able to hear it because it is at a really low frequency. Now if I increase this at like a really if I make this really high, you might be able to hear the LFO a bit. Let's see. Yeah. But yeah, so usually when you use LFOs, the intention of using LFOs is as a control signal. So now we talked about control voltage, right? So whatever the LFO is generating, it is basically a voltage, and this voltage is going from 0 to 1 to back to 0. So it is oscillating, and this oscillating voltage is really, really important for us, because now what we can do is we can use this voltage to control something else. So before I show how to modulate something, I'm going to introduce a component called the VCA, which is voltage controlled amplifier. Okay. So let's go here. We have, I'm going to move the scope here. Okay. So what I'm going to do is I'm going to take the sine wave, put it into the input of the amplifier. And from here, I'm going to put it into the mixer. So now if this is full, when I turn this, it will change the amplitude. If you want to see what this thing is doing, so instead of this, we can put this output here. And if I take this down, you can see that the size is reducing and now it is increasing. So what if we were to use the wave generated by LFO as a control signal which will modulate this knob? So we would get something, a wave which goes like this, and it will give like a tremolo effect. I think it's called tremolo. I'm bad at Western theory. But yeah. So let's try to do that. So now to modulate the VCA, what you can do is take this and put it here, exponential or linear. So right now you don't have to worry about it. But you can see now that by using this, it is oscillating. It is actually, excuse me, the voltage is changing by itself. And this is a really basic example of what you can modulate. You can basically modulate anything in here. So this is one effect that you get. Another thing that you can do here is, instead of modulating the amplitude, you could modulate the frequency, which is FM, which stands for frequency modulation. So right now I've plugged this in, but nothing is happening. The reason for that is this knob, FMCV, which means frequency modulation control voltage. So this knob controls how much of this signal is to be used to modulate the signal that this module is generating. So when I increase this, you can see the frequency is changing according to this. So these are some things that you can do. Okay, so now before we get into modulating different stuff, what I'm going to do is I'm going to show you how all these different waves are and what role harmonics play in this. So I'm going to move this here. Okay, so you can see that this is a sine wave. Then you have a triangle wave, and each of these waves has a distinct sound. So you can see that this is a triangular wave, and also here, this is a saw wave. This is a square wave. So what are these waves and how are they formed? So I told you before that a sine wave is the basic component for all pitched signals or all musical signals. So triangle wave or saw wave or square wave is nothing but sine waves of different frequencies put together. So it all comes to harmonics and which harmonics are present. So I'm going to switch to the presentation now and show you what I mean by harmonics. Okay. Okay. So harmonics is nothing but an integer multiple of a frequency. So if this is your sine wave, okay, this is just like one period of a sine wave, the which is of 50 hertz. An integer multiple of 50 hertz is 50 into 2, which is 100. So this wave, you can see, is the harmonic. And when a wave, this this is one cycle of a sine wave. So what it means is, because it is a double frequency, it is going to complete 2 cycles by the time the first cycle, this one completes 1 cycle. Similarly, the third harmonic is gonna do 1, 2, and 3. So these are based on the harmonic content, like how many harmonics are present. The sound gets a certain type of texture or timbre, to be specific. And this timbre is dependent on how many harmonics there are, which is this is the reason why a saw wave sounds different than a square wave and a triangular wave. Saw wave and triangle and square wave have different types of harmonics that are associated with it. So here, the green is the fundamental or the base frequency. So green, red, and blue, when these three are present, the wave that is generated is something like this, and which encompasses all of these harmonics and has a characteristic sound. So here you can see that if you have a square wave, you have all the odd harmonics, like the third integer multiple, fifth integer multiple, and this gives the wave this characteristic shape and that characteristic sound. And similarly, you have a harmonic spectrum where you have a sawtooth wave, where all the integer multiple harmonics are used. So this is how these waves get. Oh, this is how these waves get that characteristic sound. And knowing this is really important if you want to understand filters, like how filters work. So I'm going to put in a VCF, which is a voltage controlled filter there. And here is our basic filter. Okay, so now let's route our sine wave into the filter, and low pass, LPF stands for low pass filter, low pass it and send it out. So now, as I said, sine wave is the most basic thing. So remember this, like the more complex the wave, the better it is for the filter, or the more the filter can do. Because sine wave is just like one frequency, the filter is not gonna make that much of a difference. But if you use something like a saw wave, then you can see what happens. If I reduce this, so when I'm reducing the cutoff, it means that all the higher harmonics are getting cut. So I'm left with only less and less harmonics till the point that I'm left with only fundamentals, so which is why it looks like sort of a sine. And now, because we want to modulate everything, what we can do is something like we are going to modulate the frequency of the VCF, and if you increase this, you can see that the filter cutoff, the cutoff of the filter gets modulated. Okay. All right. So these are like the basic things. Another important concept that you need to know is the ADSR and what ADSR stands for. So ADSR stands for attack, decay, sustain, and release. And where's my browser? I'm just gonna Google ADSR because I want to show. Oh man. Wow, my computer is lagging so much right now. All right, so this is a good example. So what ADSR is it depends on, it shows the envelope of the sound. So if you think of a keyboard, when you press the key, the time it takes for the time it takes for the sound to reach its highest amplitude is called is the attack period. Then the key is still pressed. So after it reaches the highest amplitude, it falls to a certain level, and that level is defined by the sustain. So sustain is like how much once you press the key after going to the highest point, at what level should it settle? The time it takes to come to that level is called the decay period. And then once you lift the key, the release time defines how long it should take before the signal dies down. So let's try that in our VCV. So suppose I'm going to add an ADSR module here. This is an ADSR module. Okay, so we have an ADSR module, and what we want to do is sort of have something that will give you a keystroke. So a keystroke or can be emulated by, there is this thing called a gate. A gate is nothing but on or off. So you can also call a square wave as a gate. So yeah, so this is off and on, off and on. So what it will do is during the on period, ADSR will be in play, like it will be working. And when it is off, it will be like the note uh, has been released. So when it goes to on, again the note is pressed, and when it goes to off, the note has been released. So in this case, what we can do is we can use a MIDI input. MIDI CV is this module, which has a gate input. So whenever I press a key on my keyboard, the gate will be on, and when I release it, it's going to be off. So I've connected this. Let me set this to my computer keyboard. And I'm just going to press a key on my computer. So the lowest row and the top row, they act as keyboard keys. So when I press it, you can see the gate is on. When I leave it, it's off, on, off, on, off. So this will give us the gate signal, like the key on and key off thing. So now, okay, so now I'm going to plug this in here. So this tells the ADSR module when the key is pressed and when the key is not pressed. And based on that, our ADSR module will generate a voltage signal which mimics that curve. So here I'm going to, let's see what the output of the ADSR looks like. So when I press the key, you see that when I press the key, the blue is the gate and the red is the signal that the ADSR module has generated. So see, I'm still pressing the key. I leave it. Okay. Now, if I want to increase the release time, I'm going to increase the release time, and I'm going to press the key again and release. So you can see it took a bit longer. If I increase the release time even more, and now I'm still pressing the key, I'm going to release it now. You can see that it's taking even longer for it to die down. So let's see how this sounds. So So we put this in, we are still using the filter, and this is here. Okay, so now we have generated the ADSR signal. Like we have this signal, but where are we going to use the signal? This signal should, for this to work, what we want to do is we want to change the amplitude of our original signal of the sine wave according to this. Like our amplitude will increase like this, then stay at a certain level, and then when I release, it will slowly reduce. So I want to modulate my VCA. So instead, so before what we had done, we were using an LFO and the sine wave would do this. But now we are manually using a custom signal to do that. So if you put this here, this is off right now because I have not pressed any key. Now I'm going to press a key, and you can watch this one and these two scopes. So I press it, and okay, hold on. Why can I not hear this? Oh, my bad. The mixer volume was down. Okay, so I hope you can hear that. So you can see that I'm still pressing the key, and the key is still pressed, and it is staying at a certain value, and then it's going to die down. Let's actually use a saw wave because we can hear it better. Okay, so I'm going to increase the sustain a bit more. Now let's see what happens if we increase the attack. It rises really slowly. Also observe how the ADSR signal down there is changing. And this is, ADSR is a really beautiful thing. It can help you to achieve get like a really awesome, get really awesome sounds from the synthesizer. Because now if I bring the attack down to 0, see what is happening? It gives this sharp sound. Okay, so we were using a computer keyboard or basically like a MIDI keyboard to get the input. Now, instead, let's try generating constant gates. So as I said, we can use a square wave to generate a gate. So let's use the low frequency oscillator, which will generate gates like this. So these gates are passed into ADSR. So you can see. And if I increase the LFO frequency, and just notice how when I change this, I'm going to zoom in here a bit so that it's more clear. So yeah. Okay. So this is all good, but this is sounding like really monotonous, and it's just one pitch that we are using. So what if we could somehow like add some really nice tones to it, like some really nice pitches? So the way to do that is you can obviously like use a MIDI keyboard and play whatever you want, but to make it like do it on its own, what you can use is a sequencer. So I'm going to use the default sequencer, which is this one, Q3. And this sequencer has a lot of things inbuilt. So it has a gate, which you can see it is going on and off. So we don't need a LFO here. So I'm going to disconnect this. Let's use this gate. So this gate is going to help us generate the ADSR signal. Okay, good. It's doing that. Now it has 3 rows, and all of these 3 rows have 3 outputs. So what this sequencer is basically doing is going 1, 2, 3, 4, 5, 6, 7, 8, and all the way back like that. So what we want to do is this will give you what voltages all of these are generating. So if you plug this into V oct, which is voltage per octave, which controls the pitch of the VCO, then you would get sounds. Right now, all of these are turned to 0, so nothing is coming. But if I do this, oh. I'm going to reduce the clock a bit. Okay, so we have now got some sort of a sequence going on. And now, if we can mess around with these parameters. Right. So this is all good. So we are getting close. We are getting close to making a patch out of this. But right now it sounds really it's not in any key, or it sounds really weird. So going back to this whole thing about process and accepting every sound. So if you can view this as an experimental music piece, and you don't have to have it conform to all of these traditional keys and stuff. So this in itself is music, and it in itself is beautiful. But if you want to like set it to a key, there are even more modules that are available. So I'm going to use this one module called Quantum. So what Quantum does is basically it quantizes the voltage to a particular key, like to a particular note. So here you can see you have the white and black notes. So what you're going to do is I'm going to put the voltages generated by these into the quantum, and this I'm going to give out here. So when I do this, can you hear this clearly, or is it breaking? This is sound breaking. Mohit? Okay, I'm gonna proceed now. I think it is a bit okay on my side. You can see that it has conformed to this key, and then you can okay, so we have got this going, but now we have to think what else can we do? How else can we like modify this sound? So right now we are not modulating a lot of parameters. So we just have an ADSR there, and we are modulating the amplitude of the signal. We are not doing anything to the filter. The filter is just there. So what if we were to modulate this? One way that we can modulate this is use an LFO and modulate the frequency. I really hope that you can hear that, but like based on this frequency, it is modulating the cutoff of that filter. But however, something even more interesting would be if we modulated the filter using the ADSR signal. We already have this ADSR signal that is being used. So what if okay, so what if we use this signal also to modulate VCV? So now what is happening is every time you hit the note, the filter opens up, like the cutoff increases, and based on this curve, as soon as you release the key, it's gonna start coming back to its own position, and this actually creates a like really nice sound. yeah, this gives you like a really nice effect that you can use. And not just frequency, there are even so many more parameters that you can modulate like this. So right now I'm just gonna like increase the resonance here. So keep this in mind that modular synthesis is all about exploration and all about trying out different things and just finding new sounds. That's all it is about. Yeah. Okay. So I think this is like a basic, pretty okay basic patch. I'm gonna show some more things, like you can make this like really cool by adding a kick. You need a gate here, right? We can use this for now. Yeah, I think my computer is kind of not able to handle this right now with Zoom, and it is lagging. I can hit that. Okay, it was kind of better now. So right now it's just gonna play it at the same time, which is not really cool, really that great. But we could this is kind of like a bit higher level stuff, but you can just see how all of these make changes. What I'm gonna do is I'm gonna add a bit of randomness in here. So there is this thing called Bernoulli gate. What it does is it picks only some of so whatever you input into it, it will pass that based on the probability of like a heads or tails. Like if it is heads, it will pass. If it is no, it won't. So if I do this, sorry, I'm going to turn this off and even this off. So actually, I think we should hear the snare. That would be easier. Yeah, so you can hear the snare. I'm gonna put the snare into the Bernoulli gate and put this in here. So now you can see that it is not passing anything because the probability is 0. As I increase the probability, I'm increasing the probability of B. So it is letting some of those pass. So now this is giving you like a pseudo random sequence, and you can use this to generate like random time signatures, which is really cool. So if you do this for even the kick, then you get both. And you've got sick beat. Let's increase this probability. All right. Okay, I'm gonna. So yeah, this was just an example. So Mohit, how are we doing on the time? Like, we out of it? I am just gonna show you some other patches that I've worked on. I really hope that they run on my computer, like with Zoom running on. What is that? Okay, yeah, this one is pretty cool. All right, so let me just put this onto Zoom, and that's bad on my end. But what I'm basically doing here is this is a wave, like a signal generator, and this is the signal it is generating. Based on this signal, in the second scope, you can see that wherever it is, like all those planes are the different notes that it is generating. So you're getting like a random increasing kind of melody, but it also like goes up and down. And then I have a lot of kicks and snares here, but I feel like if I like unmute them, my computer is gonna crash or something. Yeah, that's really bad on my end. Okay, but yeah, that is pretty much, I think, the basics of modular synthesis. And there are like so many modules. So for example, if you see here, this even VCO, this is another type of oscillator. I'm using quantum here. This is another lateral S as a filter. You have delay, you have reverb. Like this Rampage module is one of my favorite modules. Um, yeah, basically the possibilities are endless, and you can make some really amazing stuff with modular synthesizers. Um, I would suggest that you follow some artists like modular synthesizer artists, which are really good. Okay, I'm gonna quit track. But yeah, all of these concepts of modular synthesis are, even if you are not going to be using modular synths, like knowing these concepts of the VCOs and ADSR and everything is super helpful, because it will help you, like even in DAWs, you have these instruments like in Ableton, you have the analog instrument, which is basically just a synthesizer. So even that has all of these things. But the only difference here is we make the connection in this, whereas in the analog instruments, some of the connections are already made, like the flow is already decided. But even there, you can do some customizations. And yeah, so essentially, like knowing all of these concepts and like exploring them on your own is super essential. I would say, like if you wanna get into synthesizing audio. Um, Okay, hey Mohit. So okay, guys. So I'm done with the VCV rack part of this, but I still have some more things about the of live coding that I can show you, but I'm not sure. I think I'm out of time. Am I?
No, it's okay. We have time. You can show.
Okay, that is awesome. Yeah, this is live coding is really awesome.
Kaushal, just one thing
Yeah,
that sometimes when the VCV comes in, your voice kind of crackles.
I see.
So
I'm
yeah.
okay. Yeah, I'm done with the VCV, so I won't be using VCV now.
Yeah.
I'm going to show some other things. Actually, let's go here. Yeah, so that's about modular synthesis, and next thing is live coding, which is like the thing right now, which is the geekiest music thing that you can find out there. Um, so let's just look at let's just look at this. So live coding is making music or visual art in real time using programming code. And the focus here, again, as I said, is on the process, because what you're doing in live coding is you have a computer and you sit in front of a computer. But like if you're performing with just in front of a computer, there's no interaction with the audience. That's like, it's like you're very disconnected. But what live coding does is that it displays all of that behind you, like the code is out there for the people to see. And I think that is a very important thing, because it forms this sort of a connection, like it gives the audience something to hang on. Then they can even though they can't understand the code exactly, some of it is quite intuitive, and you can see, okay, something is happening, and it is really interesting to follow this whole process of what is happening. um, so I'm going to show some two videos of live coding. So this was I actually presented a paper recently at the web audio conference, and so the experimental music community there is amazing, and I got to see this one amazing artist and a programmer who's actually a creator of one of the live coding languages called Gibber. Um, so uh, this is him performing. Okay, fine. This is not clear. Hold up. Let me redo that. Okay. So that was a really short video, but you could see like the whole code was there, and he was like sitting there and adding layers on top of it in real time. And this is another video from the conference, which is actually a lot of things going on there. There's like live coding of visuals. There's music, of course, and even more stuff going on. So let's take a look. Okay, quality set to. All right. Oh, okay. So the thing that you saw, the thing that the guy did, so he was using a device called, oh shit, I forgot the name of that device, but basically it is a device which like clamps onto your hand here, and it is able to sense the muscle, like the if you move your hands, basically it senses the changes in your, I'm not exactly sure how it works, but basically it senses your movement, and according to that, you can use that data to control music. And there is a lot of things that people do like that, and they make their own instruments based on these components. So I'm going to show some short demos of languages. So there is this one language called Orca, which is which is which is live coding language, but it is used mainly for sequencing. So this is not for sound generation, but this is for basically a sequencer, like a programming language that you can use as a sequencer. So let's switch to that. Okay, so this is Orca, and Orca cannot make sounds by itself. But basically, since it is just a sequencer, what you need to do is you need to run Ableton with it. Not Ableton, basically, you can use any sound generating source. You can also use hardware synthesizers and route the MIDI messages from Orca into Ableton. So I'm gonna perform a small composition. Shift register. Yeah. Okay. So this is a really, I mean, sound generation wise, it is not anything innovative, but the innovation, like the beautiful thing about this is the process of the sequence generation. Um, so in Orca, I'm gonna shift register. Wait, where am I? All right. Okay. Oh, my bad. Not this one. This, I need shift register. Hmm. All right. Okay. So I'll kind of try to tell you what's happening here. So what I'm doing is a shift register is something like you can store. Okay, how do I explain this? So basically, you have some notes. So in here, you have these 8 boxes, and whatever you put in the boxes, it is going to be shifted to the left by 1 position, and whatever is in the end box goes back into the first thing. So everything keeps on going like it keeps on circling. And so if you see here, this is the shift register, and F, C, E, A, G, all of these are the notes that are in the register. So what I'm going to do is, this section down here is what generates the MIDI notes, which sends the MIDI signals to Ableton. I think I need to set Ableton's device to zoom. Okay, I hope this works. So okay. Yeah, so the idea here was the same melody starts at different points. Like the first one, when the first one reaches like the second note, the second voice starts. So all of these voices start one after another. So that is the whole concept here. I'm gonna switch to the next thing. Okay, so this is Orca. Um, and what I was doing was Ableton. In Ableton, I was just using a marimba instrument. I had tweaked it a bit, like some EQing, and I had like panned the different voices in it. Okay, another example of live coding is live coding visuals, and visuals are a big part of this. So you can think of this language as a modular synthesizer language, but for visuals, because you have all of these OSC, which is an oscillator, and different functions which you can use. So if you do toggle, so what you can do here is, so this is an oscillator, and if you do this, you can see that it is white and black, which means like high and low, high and low. So this is just the same oscillator that is running. I'm gonna turn this off and show you something really cool that I made. So just to show you how all of these things work, I'm gonna comment these things out and just run the basic So this is the basic thing that is going on in the background. So if I change these values, it's going to change that. Now I'm going to add some color to this. So it's just a signal, and for that signal, it is adding on these like a modular synthesis, adding these different modules onto it. And yeah, so now this has started to change the colors. So I'm going to rotate this thing. And let's do a kaleidoscope for, okay. So yeah, you can make some really trippy stuff with this. Yeah. All right, I'm going to turn this off. But yeah, I'm not an expert in this language. I literally just have done this one example. Like, but I want to learn this language because this is awesome. And this is not just like with the visuals, but what you can do is you can route audio into it and use like the frequency content of the audio signals to like make all of these patterns go like generate all of these patterns. So you can have like a audio visual experience, which is a big part of again a live coding experience. So that's one language. This is another language called Tidal Cycles. What it does is it it is a sample based language. So you have all of these samples here, and these samples are sequenced or basically positioned in different cycles. So let me just start this thing. Okay. All right. Okay. I'm gonna actually generate a new. All right. So D1. So what I'm doing here is bass drum and snare, bass drum and snare. Even I can't hear that. Hold up. Okay, what is wrong? Hmm. Okay, I'm not exactly sure what is wrong with this. Yeah, with live coding, like there are things that can go wrong, and I'm not an expert in this. I guess that's fine. But I think, yeah, just for your reference, this is another language called Tidal Cycles. Yeah, and I think I've covered pretty much. I can like I think for just like an ending note, I can show you this thing. Um, this is a sequencer synthesizer that I had made, which is So if you can add notes onto it, and so I'm gonna add and play them. Oh wait, something is wrong with my. Yeah, I could hear it right now. If you heard just huh. I feel like I should quit Ableton. Okay. So you have all these parameters, and like behind the scenes, what is happening is it's just all the modular synthesizer things. So this is the attack. So you can see this is just a tempo. This is a filter. This is a reverb actually. Yeah. I think I can show you the title cycles now. I think this will run. All right. Nope. Okay. Yeah, I think that's fine. Yeah, but that is pretty much it. So I guess on an ending note, I would say that do like this modular synthesis is a really amazing thing, and you should definitely explore different things in it. The way to get started is just start doing it. And actually, I would recommend so on YouTube, if you search for this channel called Modular Curiosity, that's a very good series on using VCV rack and getting into modular synthesis. So that is how I learned like all like everything about modular synths. And you should check that out if you found this stuff interesting. What we did right now were like really basic things with modular synthesizers. But if you just like try to look up on YouTube or something, you'll find some really amazing stuff that people do. And with VCV Rack, you can do all of that on your computer. You don't need to spend thousands of dollars on getting all of those modules and stuff. So yeah, that's a pretty cool software to check it out. All right, thank you guys. I think I went way over time, but I hope you enjoyed this. Yeah. All right, Mohit.
Yes. Thank you, Kaushal.
Yeah, no problem.
Great session with you. And thank you for taking out the precious time even at night. It's almost morning at your.
Yeah, at 3:30. That's fine.
Yeah. But I hope our students learned a lot today, and they'll get in touch with you if they have some queries and everything. I'm sure that you'll be happy to share your knowledge to them.
Yeah, for
And
sure. Yeah, you can reach out to me. Like if you want to like actually look at my projects, you can check them out on my website. And if you want to reach me, just like email me or anything, like even
could
Facebook
you
is fine.
just
You
share your
get my
website
information
to me
from.
and
Yeah,
I'll share it to students.
I'll
What is your
send it to you, but it's basically kaushalsali.com.
okay?
Yeah, kaushalsali.com.
www.kaushalsali.com.
Did
Sessions with
so wait, I'm sharing my screen again. So this is the web address.
So we would like to stop here. Yeah. Oh yeah. Lovely. So we would like to stop over here and hope it's a great time.
Your voice is breaking up, actually. I can't hear you.
Session is actually live on YouTube. Some of you can see it. Students are asking me if it is uploaded on YouTube or not. Then it is, because and it is for our students only, so students can see it.
Okay.
Yeah.
I think there was one question. Someone is asking, how do you approach Georgia Tech? So basically what I did was I took the GRE, and basically I did this was a Master of Science in Music Technology. So you can check out Georgia Tech's website for the master's program here. There are a few more programs. Like if you get in touch with me, I can like tell you more about where all these programs are and which ones are what these programs focus on there. But yeah, that's pretty much it.
Yeah.
Yeah, I think his voice is still, Mohit, your voice is breaking up or something.
No. I just said that we'll stop here.
Oh, okay. Yeah.
Thank you all. Thank you for attending this session. Thank you, Kaushal.
All right.
Yeah.
See you guys.
Yeah.